You ready? Okay, you're good? Here we go. Friction. I taught you last year that friction is due to the molecular interlocking of these tiny microscopic hills and valleys that exist on the atomic scale between an object sitting on the surface and the surface itself, between two objects rubbing together. Even if they appear smooth, on the atomic scale, you'll find they are not. They are not. The key idea for friction in terms of direction is it resists sliding. Because of that, it can resist motion, but it can also cause motion. Example 1 says, draw a free body diagram. We'll label the direction of friction in each case. So example 1a, we have a sliding block. There's a slight typo here. Can you just pretend that that gap isn't there? I couldn't get it to vanish when I was typing this in Word. So that should be touching. It's not hovering slightly off the surface. Okay? If this block is sliding to the right, what direction will friction be pointing then? Yeah, let's label it in. What about for a car speeding up? I think I went on a big rant last year. I said many of you think that a car's engine or a car's tires are what make it go forward. And I said that can't be the case, because if you put a car on ice, it still has its engine, it still has its tires, but it ain't going forward. What force makes a car go forward? Friction. So I already can kind of, Haley, intuit that friction's going to be pointing forwards. The real question is, why? Well, if you zoom in on this tire, right here, it's pushing backwards against the pavement. It's trying to slide backwards. And because it's trying to slide backwards and friction acts in the opposite direction of sliding, which way will friction be pointing? Forwards. It's also a Newton's third law idea. The tires push backwards against the floor. What does the floor do? Pushes forwards against the tires. So I know that friction is that way. It's a tough one to wrap your brain around. Time and time again, when I'm talking to physics teachers or in textbooks, I'll often see friction on a car pointed backwards, as though somehow friction is slowing the car down. It is not. Air resistance is slowing the car down, not friction. The same for a car slowing down. Last year I would have gone on a rant. I would have said, you might think that brakes make a car slow down or tires make a car slow down. If you're on ice, you still have brakes, you still have tires. Can you slow down? No. So what's changed on ice? It's not the brakes, it's not the tires. What's changed? Friction. Friction is what makes a car slow down. How? When you press the brake pedal, Taylor, you tell your tires to apply a slight forward force to the road. They push forwards against the road. Newton's third law kicks in. Your tires push forward against the road. What does the road do? Pushes backwards against the tires. And that's why friction is pointing backwards in that situation. You'll notice in situation B, friction and motion, same direction. That's why I underlined friction resists sliding. It's often in the opposite direction of motion, but not always. You got to really dive deep. Is that okay, Moby? What does friction depend on? Last year I told you it depended on two things. It depended on the type of surfaces that are in contact, and this is represented by the coefficient of friction, symbol mu. The coefficient of friction has no units, no dimensions. It's a ratio that describes how sticky objects are compared to each other. Ice has a coefficient of friction of near 0. Don't need to circle that, I'm just doing that so it highlights. Rubber on concrete has a coefficient of friction of about 0.75. So the coefficient of friction, you can think about it as a measure of an object's stickiness with an I. Or you can think of it as a measure of an object's slipperiness. If mu is small, it's It's measuring how slippery an object is. If mu is high, it's measuring how sticky an object is, but it's really measuring the same thing. That lets us take into account different surfaces with relation to each other. The second thing that friction depends on is how heavy an object is. It's much tougher to slide heavier objects. And at first glance, you might be tempted to say, Jaden, oh, that's mg, that's gravity. But we also want to explain why it is that even if an object is heavy, if you lift up on it while you're trying to slide it, it slides easier. If you push down on it when you're trying to slide it, it becomes more difficult to slide. Its mass hasn't changed. Who remembers what force did we say was a better indication to use for friction? Not how heavy it is, not mg, but what? Normal force. It's the force that surfaces push together with the normal force. And this is why the equation that you got last year, it is on your formula sheet, but we'll put it in the box here. Friction is mu times the normal force. If you happen to have your formula sheet on you, you'll notice we've just finished every equation in forces. Patrick, if you look under Unit 2 Vector Dynamics, there's only two equations. F net equals ma, yes?
Yep.
And friction equals mu times the normal force, yes? Is there anything else?
Fg equals mg.
I really put that on there?
Yeah.
Wow, that was nice of me. But we've done that already too. Everything we're going to be doing for the next while is going to be clever applications. So, here's our little thought experiment. Consider the block below, which is being pulled by student number 1. Let's make it Jaden. And instead of a block, let's pretend it's the gym benches, those benches in the gym that you can slide across the gym floor with some difficulty. So let's suppose, Jaden, you're pushing the bench across the floor. Rough surface, that's code. Whenever I say rough, what I really mean is include friction. But there's a two-word key phrase here that I should underline. You're pushing it at a constant speed. Can you imagine that? Pushing it at a constant speed. And then student number 2, Patrick, comes along and pushes down on the block. You know what? Let's pretend he sits on the bench. Okay? Language. If student number 1 maintains that, if Jaden maintains that same constant applied force, what happens to the, and let's label this part A, weight, part B, normal force, part C, friction, and part D, motion of the block. We'll label them A, B, C, and D. So the first question is this. What happens to the weight of the block? First of all, when I say weight, what am I really talking about as a force? What's it a synonym for? Taylor, you're right. I read your lips. I think you're right. Yep. So mg. When Patrick sits on the bench, and we're only talking about the bench now. Look at the bench. Look at the bench. Look at the bench. Did the mass of the bench change? No. Did gravity change? No. So the weight mg stays the same. B. Normal force. What happens to the normal force when Patrick sits on the bench? Let's convince ourselves. Over on the left, I have a free body diagram. This is the situation when you're pushing at a constant speed. The only thing that I don't like is looking at the arrows. It looks like the normal force arrow is longer than the mg arrow. To me, it should kind of be chopped off, but don't worry about fixing that. I know that normal force and mg are the same in situation number 1. In situation number 2, I still have mg down, but because there's that extra push down, the normal force has to be way larger. It's going to cancel out mg of the bench, and it's got to cancel out Patrick's mg, Patrick's weight. That's the force downwards. Oh, and I would have friction that way. So based on that, what happens to the normal force when Patrick sits on it? And my abbreviation for gets bigger is an arrow pointing up. Increases. If the normal force increases, what happens to the force of friction? Well, friction is what times what? Mu times the normal force. If the normal force got bigger, what's got to happen to friction? Get bigger? Increases. And so, what happens to the motion of the block? Well, if friction gets bigger, really now my free body diagram looks more like that. In that free body diagram, who's winning? So, is my object going to be speeding up, slowing down, or going at a constant speed? Slowing down. I think the motion would be slows and eventually comes to a stop. Now, in this analogy, this situation that I made up, that would happen really, really quick, I think. As soon as Patrick sat on it, would you come to a stop really, really quick? But I know that I can write slows, stops. Once we stop, is this free body diagram still correct? Why can't it be correct anymore? That would be going backwards. So as soon as we stop, then friction becomes just as big as it needs to be. Then friction suddenly goes back to matching the applied force. And that's why friction is a bit of a strange force. It's as big as it needs to be until you beat it. So I'll leave my diagram like that, but I just want to point out that for what it's worth, that would no longer be the case once we came to a stop. It says, explain your answer. Oh, don't do that, Mr. Duick. Explain your answer. I think we just kind of did right there. I'm pretty good with that. So friction is what times what? Mu times the normal force. If I want to get mu by itself, divide by the normal force. Here's our next little thought experiment. It says this. A student gives an old shopping cart a big push on a flat, rough surface. When I say rough, we really can mean to ourselves friction. Which of the following is the best force diagram for the cart after the student has released it? Let me pause the video for 1 second. We got 4 choices. We get to vote. Once again, high, hold your hand up so how sure you are of the answer. So there's 4 possible free body diagrams. Who says, got to be A, Mr. Duick? A, got to be A. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's peer pressure. 12, 13, 14, 15, 16. Who says B? Got to be B. 1. Who says C? I'm liking C. Who says got to be D? Mr. Duke is moving forward. Got to be D. So as always, you can attack or defend. You can convince me that you're right or that other answers must be wrong. Convince me. Jaden. First of all, what's your argument or point? What are we going with? Are you defending?
I'm attacking B.
Okay. Why do you think B has to be wrong?
Because B has to be wrong because the chair is slowing down and the applied force is bigger than friction.
Okay,
and then
so
D is also wrong because the chair is slowing down but there's no friction. So
those two would not slow down.
yeah, and
They would either speed up, or in B, if the arrows were the same length, they could be going at a constant speed. C?
C would just keep going because there's no force.
Constant speed,
Yeah.
horizontally. So which one must be right? Has to be A. Which law did he use? The one that talks about acceleration and unbalanced forces. Which law did you pull out of your back pocket there? You know what Newton's third is? Forces come in. What's Newton's third? Nothing? Wow. Tough. Okay. Forces come in. Okay. I might have showed it to some classes last year. I don't know.
I never saw it till now.
I didn't see that last year.
Okay. And by the way, that explanation, Newton's first, I'd take that because you'd be saying, Mr. Duick. Now, the longer version is The only way we can be slowing down, let me phrase that differently, the only way we can be accelerating to the left is if we have an unbalanced force pointing to the left. The only diagram that works for is A. Okay? Example 5 says this. For each of the blocks below, write a vertical force equation. Find the force of friction. Write a horizontal force equation. And then find the acceleration. I like this question. I like this question. Although I probably would just ask part D and I wouldn't walk you through all of these steps. And I got to be honest, the left-hand side is too easy for Physics 12. The right-hand side is barely scratching the surface of Physics 12. Since we're going to do the same question but twice, I'm just going to draw a little line down the middle of the page like that. You know, before I even dive in here, I think this is a job for a free body diagram. So on the left-hand side here, I'll represent the mass with a dot. What are the forces acting on this 10 kilogram mass? Get the obvious one. Gravity down. Is it sinking into the ground like quicksand? Is it flying to like Superman? Now we're going to add a third check mark. Are there any other vertical forces? And this year you're going to find a lot of the time there will be. So that's the habit you want to double check. Are there any other vertical forces in the left-hand side? No. Then what can I say? I can say the normal force has to be the same size as mg. Looks like there's an applied force of 20. That can be a little invisible leprechaun or angel or something off the screen. Is there friction in this question? How do I know? Okay. Hey, what's mu? I don't know. What's mu with you? I gave you a mu. I'm going to guess that friction is smaller than F applied. If I'm wrong, I'll notice that later and I'll fix it. What about the right-hand side? What are the forces acting on it? Get the obvious one. Gravity down. Is it sinking into the ground like quicksand? Is it flying to like Superman? Are there any other vertical forces? What? Well, there's also a 15 newtons. So what can you tell me about my normal force, Patrick? Will it be the same size as mg? Good. I'll exaggerate it so it's obvious. What else? Looks like we have an applied force of 20. Which way would friction be acting here? To the left. Probably bigger than the last one, but I'll gamble that it's still smaller than the 20. I'm not sure. I've got to run some numbers. Okay. Cool. Part A. Part A. Tato, what does Part A want me to do? In the left-hand situation, what's the vertical force equation? Yeah. Now, I love the fact that you jumped right to the punchline. Hopefully you said, is it sinking in the ground like, is it flying? You're like, no, it's not accelerating vertically. That means the net force is 0. So you could go winner minus loser equals 0. Or the shortcut now is just to say everything up equals everything down. So you said Fn equals mg. Good. Hey, Tato, what about the second diagram? Just write me a vertical force equation. And the easiest one, if you're not sinking or taking off, if you're not accelerating, everything up equals everything down. Everything up, Fn, equals everything down. Yep. And then I can get whatever I need to by itself. Cool. Cool, 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 cool. Paige, what does B want me to find? Well, friction is mu times the normal force. And on the right-hand side, friction is mu times the normal force. Do a quick double check. Paige, did they tell me mu? Oh, I don't know the normal force. Oh, but look, 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 look. I know another force the same size as the normal force. mg. Okay, so this is going to be mu mg. Let's plug in numbers. Friction is going to be 0.12 times 10 times 9.8. Oh, I can do this in my head. It's going to be 98 times 0.12. It's going to be 9.8 plus 1.96. It's going to be 10.8, 11.76. Double check me. Yeah? And then I'll go to 3 sig figs, 11.8, and it's a force newtons. Is that okay, Paige? On the right-hand side, they want me to find friction. You said friction is mu times the normal force. I don't know the normal force. Oh, but look. I have a more complicated free body diagram, but I can still figure out the normal force. The fact that I have it written right here helps, but even if I didn't have it written right here, I could probably figure it out from there by just saying, hey, everything up has to equal everything down. So it's going to look like this. Friction equals mu bracket mg plus 15. Which is going to be 0.12, 10 times 9.8 plus 15. Do that one in your head, Mr. Dewick? Oh, maybe. 10 times 9.8 is 98, plus 15 is going to be 113. Oh, yeah, I can do this. 0.12 times 113, it's going to be 11 plus 2.6. 13.6. I'm missing a digit. What is it? 113, Mr. Dewick. So 11.3 plus 2.26. So it's going to be 13.56. There we go. If I wanted to go to 3 sig figs, 13.6. Linnea, what does C want me to do? That's physics speak for who's winning? On the left-hand side, who's winning? Who's losing? Equals? And I think on the right-hand side, don't you actually get the exact same equation? What's going to change on the right-hand side is friction is going to be different. Sharon, my joy, what's D want me to find? How would I get the A by itself in this equation here? Divide by M? Divide by M, okay. And again, Sharon, you'll notice I actually get the same equation each time. I get A equals F applied minus friction over M. I get A equals F applied minus friction over M. And all it's going to change is the numbers. So it was 20 minus 11.76 divided by 10. Oh, dividing by 10, I can do that. Anybody can do that. 20 take away 11 is 9. Take away 0.7 is 8.3. 8.24. 0.824? Double check me. Is it 0.824? Yeah? And it would be meters per second squared. Here, it's going to be 20 take away 13.56 divided by 10. Linnea, my joy, are you ready? I do it like this. 20 take away 13. That I can do in my head. 7. Take away 0.5, 6.5. Take away the 6, 6.44 divided by 10.644. If you haven't figured it out, by the way, when you're doing math by hand, you start on the right and work your way left. But when you're doing your math in your head, you always start on the left and work your way towards the right. 0.644, isn't it? Is that okay? What else could I have asked? I could have given you the acceleration and said, find the coefficient of friction. That would mean getting the mu by itself. Now here, because we had crunched friction ahead of time, we dropped the number in, but if we had dropped in friction equals mu times the normal force, we just get the mu by itself. There can be friction on an object even when it's at rest. In fact, there's two types of friction. There's what's called static friction, and there's what's called kinetic friction, and that's the little rant I go on right here. Static friction, you may have noticed, if you're ever moving something really, really heavy, Patrick, getting it moving is tough, keeping it moving is easier. It's because there's two mu's. There's what we call a mu static, and it's the maximum. Once you get it moving, there's a mu kinetic. Now, having said that, we're going to treat them as though they're the same thing, even though they're technically not. We're going to just say there's one type of friction. In example 7, I'll walk you through how you would handle it if there's both types, and I'll give you one from the homework. But I'm trying to recall, I think on your test or in the future, I just talk about one type of friction. But here's what I want you to notice. Suppose I pull on a desk with a force of 2 newtons, and the desk does not move. Which of the following is true? A, static friction is bigger than 2 newtons. B, static friction is exactly 2 newtons. C, static friction is less than 2 newtons. Or D, there is no static friction. Mr. Dewick? Yes, Alec. Can we vote again? Sure we can. Since we've got 4 choices. Absolutely. So I'd like you to imagine I pull on a desk with 2 newtons of force. The desk does not move. What can we say? Who says, Dewick, static friction is bigger than 2 newtons because it's not moving? 1, 2, 3. 3. Might be right. Who says, Dewick, static friction is exactly 2 newtons? 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Who says, Mr. Dewick, static friction is less than 2 newtons? Who says there's no static friction? Alec, why did you say, oh yeah, it totally is part B? Can you use the word that begins with the letter A? If the forces aren't balanced, it must accelerate. That's the power of Newton's first law. So if friction was bigger than 2 newtons, that would allow me to tug on Alec's table, let go, and it would slingshot, knocking him over and then smacking into the far wall. I'm kind of disappointed that it doesn't, but it clearly doesn't. Oh, and if friction was less than 2 newtons, it would accelerate my way. It's got to be an equilibrium. There's our fancy word. The net force has to be 0. Last year I would have said the forces are, I'm looking for a word that begins with letter B, and you would have said balanced. Why? Because it's not accelerating. What law was that? Newton's third is forces come in pairs. This is the one that says if you're not accelerating, the net force is 0. If you are accelerating, the net force can't be 0. Or you can also reverse it. If the net force isn't 0, you must be accelerating. And that's what Alex suddenly went, oh! If the net force, by the way, A, C, and D really are different ways of making the net force not 0, not balanced, in which case you must be accelerating. And the question clearly says you're not, does not move. Is that okay? Make sure I show you this here video here, but I'm going to need to delete this for room. So I got a new video and I've added it to my notes, but I forgot to add it to your copy when I photocopied. Here is an example of the 2 types of friction. So it says an object sits on a surface and there's 2 coefficients of frictions. There's mu static, which is the maximum, 0.3. And then there's a coefficient of friction kinetic. Once you get it moving, mu is 0.25. So the first question asks, determine the force required to move the object. You know what? This is a job for a free body diagram. We have gravity down, normal force up. I don't see any indication of other vertical forces. when you're not moving, the friction that we're dealing with is static friction. And continuing on from the previous example, for me to get it to accelerate, that means the applied force must be the same size or bigger than static friction. You okay with that, Ira? In other words, my argument for part A is when it says, what's the force required to move the object? The force you're going to need to apply is friction, but it's going to be static friction, which is going to be mu s times the normal force. The one that's tougher to move. I don't know the normal force. Oh, but look. Another force the same size as the normal force. What? Here, no other vertical forces. So, to start it moving, the coefficient of static friction is 0.3, and then it's going to be 5 times 9.8. 1.4 something. I'll tell you that much. 1.4. It is going to be 1 point something.
Yeah, 14.
You missed a decimal, I'm sure of it.
Yeah.
14?
Yeah.
Oh, no, you're right. I'm sorry. You're right. I'm doing it wrong in my head. I missed the decimal. 14.9 newtons? Sorry, 14.7 newtons? Okay. What if you pull with 14.6 newtons? What will happen? Nothing. What if you pull with 5 newtons? What will happen? Nothing. Or, part B. What if we pull with 10 newtons? What's the acceleration if we pull with 10 newtons? And then it says find the force of friction. What's the force of friction if I pull with 10 newtons? Why can't it be 14.7? Then be going backwards. And this is where friction, static friction in particular, is as big as it needs to be. It will only, excuse me as I cough, Kieran, it will only match what you're doing. So if I'm pulling with 10 newtons, friction is 10 newtons. What if I pull with 12 newtons? How big is static friction? What if I pull with 14.6 newtons? How big is static friction? And you, right around 14.6, you would start to feel through your hands that the object was just ready to go. You can try that sometime with a desk. If you slowly increase the force, you'll be able to feel when it's just ready to start going. What am I pulling with in part C? How many newtons? It's going to accelerate. So, looking at my free body diagram, who will be winning? On my diagram, force applied? Yep. Who will be losing? Friction, except now it's going to be the kinetic friction because now we're moving. And that equals MA. How would I get the A by itself? So it's going to be applied 20 minus mu K mg divided by 5. It's going to be 20 minus 0.25 times 5 times 9.8 divided by 5. What do you get for the acceleration? Anyone else? 1.55? By the way, what's the force of kinetic friction? Because that's the other thing it asks, is it find the force of friction and the acceleration. Well, that's going to be mu K times the normal force. The kinetic mu, the one that you use once you're moving, it's going to be 0.25 times 5 times 9.8. What do you get? Anyone. So it's going to be 0.25 times the normal force. I don't know the normal force. Oh, but look. I missed the 2. 0.25 times 5 times 9.8. So to get this thing moving, I had to pull with how many newtons of force? 14.7. To keep it moving at a constant speed, how many newtons of force? And that's what explains why when you're moving something that's really heavy, getting it moving is tougher, keeping it moving is slightly easier, because there's two different coefficients of friction. Now, I'm not going to do a big song and dance about that on a quiz or a test. There is, I think, 1 or 2 questions in the homework that are talking about the difference, okay? What's your homework? Here's what I assigned my block E's. One of your Rising 7, you can cross out 8. Cross out 8. You can cross out number 11. You can cross out number 13. 15 is cool, but I'll nuke it. You can cross out 15, 17, and 18. So let me add that to my sheet here. So what did I assign? I assigned 1, 2, 3, 4, 5, 6, 7. I skipped 8. 9 I did. I assigned 10. I skipped 11. I assigned 12. I skipped 13. I assigned 14. I skipped 15. I assigned skipped 16. I skipped 17 and 18.